And today we're happy to have Sasha Goncharov as a speaker who will speak about non-commutative cluster Lagrangians. Sasha, please.
Yes, thank you for giving me a chance to talk, for the invitation. So I'm going to talk about joint work with Maxim Kontsevich. It's actually on the web. And I'm going to follow closely some parts of what's written on the web. Uh, so uh, mm, First of all, let me give you some motivation. So if you just start from a surface, and have, I wrote split semi-simple group, but you can take PGL2, for example. Then you have moduli space of this G local system on S, just flat G connections on S. And it's very well known that this space is symplectic. It is also very well known that you can produce Lagrangians in the following way. So you start with a threefold M, which has your surface as a boundary, and then you just consider those local systems which extend to M. So in other words, you consider all local systems on your manifold, and there is a restriction, so you take the image of the restriction functor. Now, so far so good. What if you want to consider somewhat more general symplectic spaces or Poisson spaces? And definitely the one which comes next is the following. So we take a surface with punctures, bigger than zero punctures. And then we have monodromy of this flat connection. That's my map mu. So the monodromy takes values in the Cartan group modular action of the Yale group for each puncture. And it's a Poisson space, but we can produce generic symplectic leaves by taking semi-simple parts of the monodromies, I mean diagonal part of the monodromy matrix around the punctures. So if we indeed take a fiber of such a map over a certain point, we get a symplectic space, and I'm interested in the specific one where I take pre-image of the unit element in the Cartan group. And so this is my space of G-local systems with unipotent monodromies. It's symplectic. Now let's try to imitate what we did just a minute ago. So we take a three manifold. And three manifold is a three manifold, so it's a boundary as a surface, not punctured surface, but a surface, compact surface. We call it S bar. But we assume that our surface is obtained from this boundary by deleting a few points. And the question is, can we get in a similar matter some Lagrangian in this symplectic space? Well, what if we try to imitate what we did? So the answer is going to be no, that what we did before doesn't help. For example, you take a ball and this ball-bound sphere, we deleted several points, for example, 4 points from the sphere. And then we try to find Lagrangian. So what we get, count shows that if we delete, for example, 4 points here, and consider this space which I was talking about with unipotent monodromies, is going to have dimension 2. So we are looking for something one-dimensional, but G-local systems on the ball do not give you anything because there's simply none. So there seems to be no...
Sasha, I am confused. If you mark points on the boundary, so, I mean, at least physicists would consider Wilson lines, some
What?
Wilson lines, some lines inside of your three manifold. It's not
This
just...
also will not help, because if you take some lines which connect, so you're talking about sphere, so take points, you consider some lines which inside of the manifold, but then if you remove them, the boundary of what you get is something else. It's not your sphere. So you
I
can...
don't understand. I would consider something inside of three manifold can speculate, but probably you know
I
better.
guess what you're saying is, if I can guess correctly, so you're saying that we have 4 points, let's connect them by lines which lie inside of the disk, inside of the ball. And that's considered local systems which are defined everywhere except those
Yeah,
lines.
something
But
like
then
that.
the boundary of this is not what we wanted. The boundary of this, as little exercise shows, in this case, it will be sphere with two handles. It's a
Okay.
different space. So we're not going to get. We have this elementary two-dimensional symplectic space, and I want to get some Lagrangian inside. And it seems to be that there is no way. This, okay. So now we are going to fix this. So what I'm telling you right now, what is pre-recorded, is actually kind of exists for about 20 years. In particular, it's written in our work with, in the beginning of the work with Dimofte and Gabriele and myself. And so the recipe is the following. So we start with not just local system, but we take some extra data. We say that we have specified reduction of my G-local system to Borel subgroup near each puncture. And so this is a space which we considered with fog, and for GLN, and we proved that it is Poisson, cluster Poisson. And later we extended with Shen to the case of arbitrary group G. So this is a nice Poisson variety. And there is a similar data, so it's actually not that much bigger. It's of the same dimension as the original one. Because if you take generic G-local system, I just added for PGLN, I just added n factorial choices for each puncture. So it's just a generically finite cover. So it's a Poisson space, and there are monodromies. Now they go to Cartan group for each puncture, because you just take the eigen values of the monodromy. And if you take eigenvalues 1, then you get the space which you want to consider. And then there is a theorem, which is not at all a trivial theorem, which says that this space is K2 symplectic. Now, two things. First of all, this space is K2 symplectic. This follows from the existence of cluster structure. It doesn't follow from anything else, as far as I know. And then the Lagrangian, which I'm going to talk about in a second, turns out to be K2 Lagrangian. So how we construct this Lagrangian? We do exactly the same thing as before. We consider we consider a threefold M, such that the boundary of this M is our S completed. And then we consider all G local systems, which can be on actually S, on punctured thing, with reduction to Borel, which can be extended inside, but naturally inside you also consider G-local systems with fixed reduction to Borel near the punctures on the boundary. Is that clear? There's somehow a statement that we got a space which I claim is K2 Lagrangian. And it's instructive to look, I skip a little bit the history, so I look at the example. So what happens if you have PGL2? Then you're talking about sphere minus 4 punctures. So let's make them just 4, clearly 4. And we have ball. And then what I'm talking about, it's a G-local systems on a ball, but there's just one trivial. But now it comes with additional data, which includes choice of invariant flag, in this case, point on P1 for each puncture. Altogether, we get configuration of 4 points, meaning P1 raised to power 4. Modulus the action of the group PGL2 because my bundle is trivial, but still it's automorphism groups on the whole thing. And so one can see that this something is one-dimensional. It's obvious. And it lives inside of this guy, which is two-dimensional. And so it's obviously Lagrangian. There is nothing to check here because anything one-dimensional in two-dimensional symplectic is Lagrangian. However, the non-trivial statement is that it's K2 Lagrangian. And it's not that easy to see. So here I need to say a little bit about this K2 Lagrangians. So first of all, what is K2? K2 is a Milnor group K2 of a field. It's defined as follows. So you take F star cross F star, tensor product of two abelian groups, this multiplicative group and this multiplicative group. And then for each point over F, even infinity, you produce expression 1 minus z of hz. If this infinity just dies, pay no attention. If z is 1, it also goes to 0. But if z is 0, also goes to 0. But for all other numbers in your elements of your field, which are neither 0 or 1, you consider this expression, which is called the Steinberg element. And then, by the well-known result, if you consider cokernel of this map, then by result or by definition, this is a group K2 of F. These days, it's a result of Matsumoto because K2 of F is defined differently by Quillen. Now, what are we talking when we say that we have space which is K2 symplectic? This means the following, that we have some data on my surface, like triangulations for PGL2. And then we can introduce cluster Poisson coordinates in general. And so we get some space of where these coordinates are coordinates. But then I restrict to my unipotent local systems. So, and in this case, it's not just symplectic, but there is some expression like that. So this is important, what kind of expression. So you have expression like that. And this expression gives you eventually two form because you consider for each expression xi which xj, you can consider differential of the logarithm xi which differential of the logarithm xj, and then take the sum of this delta ij, which is usually integers. And so forms we can get this way, they are by definition K2 symplectic, but that's not the whole story. Because I mean, they are K2 symplectic, but in our story, we want to have some Lagrangian. And the condition that my subspace is Lagrangian, as I said, is not just that the two form vanishes. It's much stronger condition that it vanishes in a precise way, that it's written as a sum of the Steinberg elements, which you see here. So if this happens, you say that this is K2 Lagrangian. Now, what are the benefits of this? There are several benefits, so I'll start with what I wrote in the end of the three things. One of these benefits is that on this Lagrangian there is a canonical, essential, almost canonical function. Almost because it depends on this cluster which I choose in the beginning. But other than that, this function is sum of the logarithms of these elements which make your element in lambda 2 sum of Steinberg relations. So each of these f's give you function which is the logarithm of this f. Is that clear so far?
Sash, you could of course go faster, but I told you, I mean, it's clear module for those people who knew that before. I don't think that for people who see it for the first time, it's kind of very clear. But how many prepared pages do you have?
Oh my goodness.
Yeah, I warn you. I warned you that it's better.
I'm going to stop. I'm going to stop when you want, but I want to that people understand what we're talking about.
So okay, so we can ask someone.
That's why I made a stop here.
Yeah, all right. So it's a good time to ask questions because Sasha kind of he violated the rules and he had some prepared notes which he didn't send in advance. So any questions? So should we?
Okay, so I do have a question. Can you just repeat this K2 group? The F here is what? It's a field. Giving any field,
So you take any field, and then you consider exterior product, you can even take tensor product, will be the same answer.
You take the multiplicative group of the field and
Yes.
do this exterior product as a abelian group.
Yes. And then there is this kind of pretty ridiculous elements there, which are called Steinberg elements. So written this way. And I consider the quotient model all the Steinberg elements. So that's how it was.
So that gives the K2 group.
Yes, that's by definition in end of 60s or by theorem when you have a different definition, this is a group K2 of a field. Now, how we apply this to varieties? So for varieties, a natural field is a field of functions.
I see. Okay, that's what I was thinking.
So if you take, you see this field of functions, that's going to be our F. And so if you apply this construction to the field of functions, we get K2. But what we are looking for, we are not yet going to K2. We are going just to which square of the multiplicative group of this field of functions. And we say that, okay, let's suppose that we have some element there. I call it W. Then this element immediately produces the two form by this rule. You just apply
the forms are actually taking over scalar rational numbers, right?
I mean, it's variety, let's say, of rational numbers.
Assume that all those are
differential forms
varieties with the F being the function field.
Yes. So this xi becomes functional on your manifold. So d log xi is dxi divided by xi. So it's one form with logarithmic singularities and the coefficient 1 at this moment. But you can add rational coefficients. So those forms are the one which will appear if you're talking about this structure for manifold. And I emphasize that that's already non-trivial condition on symplectic structure, very non-trivial condition. But when you go to Lagrangian subspaces, it's even more non-trivial, because even when your subspace is one-dimensional, and so the Lagrangian property is trivial, this condition is highly non-trivial. Okay?
Okay, thank you.
So there is also question about reference to your paper with Dimovta. Can someone put? All right, so just go to archive and type any of the names.
But you better take our paper with Fogg in 2003 and go to chapter 12. It's all discussed there. Chapter 12 or maybe...
No, it's probably a question about a different part of your talk, or other remark. You mentioned paper with Dimovta.
I mentioned this idea, that it's a crucial idea, that when you look the surface with punctures, for example, sphere minus punctures, if you try to produce Lagrangian by the same construction extended inside, then you find nothing, because there are no bundles, or at least usually there are few bundles.
Yeah, but you can impose parabolic structure. There are ways to produce
No, not there are ways. There is one way how you do this.
Can you prove that there is only one way?
Yeah, I'm not saying that I can prove, and actually this is not my goal. I'm saying that there is one way which seems to be natural. This is the way when you include this reduction to Borel. And why this is natural? For several reasons. So first of all, the space which you get becomes cluster Poisson. If you don't put this reduction to Borel, it's not cluster at all. It doesn't have coordinates and so on and so forth.
But if you care about K2 structures, of course you cannot do anything, probably, I can guess, without cluster coordinates. But if you care about producing Lagrangian, I don't know, like Vitya Ginsburg long ago, I don't remember how many, he proved that the nilpotent Cohen Hitchin system is Lagrangian. I mean, reducing to Borel. So if you just remove your restrictions for K2 structures, probably it's kind of, it makes things...
If I remove this condition, then I just given this example. If you consider the case of GL2 and sphere minus 4 punctures, then the space you get is two-dimensional. So any curve on the space will do it.
Great. All right, go Go
Okay.
on.
But if I want to use the construction which I used before, extend inside, then you get nothing. And if you add framing, this reduction to Borel, then suddenly Lagrangian appears, because it appears as follows: the local system is trivial. So originally it is just a point in moduli space. But the reduction to Borel gives you variety. In this case, it's one-dimensional and configuration of 4 points on P1. And this variety is K2 Lagrangian. And as I said, that's not completely trivial fact. Not trivial at all, I would say. But that's what's happening. Okay? So we discussed what is a Lagrangian, what's K2 Lagrangian. Now I wanted to say, just a second. So what this K2 Lagrangian property buys for us? So first of all, it's a claim that if you have any variety with K2 symplectic form, by applying the so-called simple model of Beilinson and Deligne, you get line bundle with connection. So you have line bundle with connection. Now, if you restrict this line bundle with connection, and its curvature is the original, is a two form which was the symplectic form. Now, the property of K2 Lagrangian implies that not only this line bundle becomes trivial when you restrict it to this Lagrangian, it becomes trivialized, canonically trivialized. And in particular, we have the statement about functions, which I said in the beginning. Okay, so that's all kind of foundation, I mean, motivations. So what we learned is that there are some varieties which are cluster symplectic, for example, or cluster Poisson. And if you want to talk about Lagrangians, then you see example where it seems to be that this is a good example of Lagrangian subvariety in cluster variety, but it's necessary that it's K2, it's one of the conditions that's a cluster. I didn't define what is cluster Lagrange. I'll just give you one example. Okay, so the next question comes how you construct this K2 Lagrangians in general, because they come, it's not just Lagrangians, they come with some data, and which is very interesting. And moreover, not only how you construct them, but it turns out that you can do this in the situation when you are not over complex numbers, but over arbitrary non-commutative field. So now I start part 2, where I go to the work with Maxim. And so we are talking about this non-commutative cluster Lagrangians. But first of all, I have some kind of background. So I want to talk about categories and stacks assigned to singular subsets, singular Lagrangian subsets. In some symplectic M. So before the first 20 minutes or 20 something minutes, we wanted to understand everything to the bottom. Now it will be impossible to understand everything to the bottom. So, but I need to say this because otherwise it is hard to keep track of what the goals are and what are we doing. So just I say a few properties of this object categories and stacks assigned to singular Lagrangian subsets, but I'm not going to discuss at all how you construct it and so on.
Sash, before you start, so your ground field, kind of arbitrary field of characteristic 0, or you work over Z, or what?
At this particular moment, I work over complex numbers. I can work over field of characteristic 0.
M, which means that M is a complex manifold.
No. At this moment, I'm talking about a real, this is a real manifold.
Real symplectic manifold, singular Lagrangian
Yeah, just a geometric situation. Yes.
well, there are many proposals how to do that.
I think there was a proposal by Maxim Kontsevich, and this proposal has been realized by the work of a team of 3 people. This is one of the things you referred to, right? It's Ganatra.
Yeah, GPS, this Ganatra Parganshenda, that's
GPS.
and many other people, but it's kind of since original proposal of Maxim, it's been generalized enormously. So I believe that the whole theory of this microlocal sheaves, like including Shend and Adler, I mean, many people anyway, it's in that direction, yeah?
That's exactly what I'm talking about. But I
Yeah,
thought,
all right.
I thought
And
if I just refer to GPS, as you said, that's a good reference for which describes all I need. But
okay.
there were before there were Troeman, Zaslav, Schende, Williams. There was some work before that.
Yeah, the original idea, I mean, it's people went from that
I think
way,
the original idea
very
was
far.
talk of Kontsevich that are by Stagon 20
Exactly, yeah.
ago.
But another thing is that there is a conjecture in symplectic topology, if I remember correctly, that any singular Lagrangian subset has a Liouville neighborhood, which is open, maybe not true, but if it exists, then there is no question how to construct
Okay, but
such a
I need to describe this background just for you to motivate and to understand where it goes.
all right.
I'm going to talk about symplectic and Lagrangian subsets, which are super simple from this general point of view. My variety will be cotangent bundle of something, and this something will be no more than 3-dimensional. And my Lagrangians will be conormal bundle to something, and this something will be non-singular surfaces or curves. So it's definitely...
Yeah, okay. And yeah, all right.
So, but again, so my feeling is that unless I say
Yeah, go, yeah, sorry.
you're going to be lost in kind of...
Yeah, okay.
Okay. So now we have this closed Lagrangian L, which sits inside of this symplectic manifold, as I said. And then the first idea is that one assign to this some sheaf of categories. And I'm saying again, so the work is kind of sort of elementary, and it produces something very concrete and non-trivial. But to understand somehow what is going on, it is much better to have general picture, even if this picture is conjectural. So it is actually not conjectural, but it doesn't matter. It's just for motivation. Okay, so there is a sheaf of categories called C sub L on this Lagrangian. And it has some properties, but the important are the following. That first of all, if you have some open subsets in this L, so it's open and can be smoothified to a piece of manifold. Smoothified to a manifold. Any open like that, then you know what you're talking about. Then in this case, if you take, if you take this category and take its sections over this U, then this is a category which you know and like. This is just a category of complexes of local systems. On this U. All right. Then another thing which is very useful to note is the following, that if you take this category and restrict it to something which looks like graph with one vertex, edges cyclically oriented, and you have n edges, and you multiply this to disk of dimension m minus 1, because m dimension of the space, So you added some singularity, which is basically in two-dimensional symplectic space, and multiplied by something nice. So then this is dB of representations of A, M, N, not M, N minus 1 quiver N minus 1. So that's also important. Other than that, there will be nothing more complicated than that. Then the next thing is that if you have such a Lagrangian L, then you assign to this something which is first of all Lagrangian, but of dimension 1 less. And this is boundary of the original Lagrangian at infinity, whatever this means. And we have this category, so we have the category which I assign to L, and we have the category which we can assign to boundary at infinity of L. I'm not going to keep this infinity, just boundary of L. And then there is a restriction functor from one sheaf of categories to another sheaf of categories. And this is all I need from this kind of background. And so from now on, we restrict to very simple situation.
Sorry.
Yes.
Yeah, I understand that you're not very precise here. This is fine. But you said that to L you assign, it's part of the data, the category assigned to the boundary, yeah?
No. First of all, what is boundary at infinity was not defined.
Yeah, but somehow one can imagine, because this
yes,
consider with the same Maxim, the same situation in the framework of cotangent bundle to surfaces, not to three manifolds. And so the boundary at infinity of a Lagrangian is contact. Well, Legendrian in a contact manifold, but this category is something which one has to construct, because GPS, they did not care much about that. It's more like Zaslow, Truman, Schende, they care more.
Anyway, so we have this is part 2 of our work with Maximo's second paper. In the first, we constructed something very explicit. We call this admissible DJ sheaves, and that's what we work with. So this is the category, and we don't need any general machine here, but there is a construction which is very, very elementary, but let's not go into these details. What I want to say is that from now on, this L is something like cotangent bundle to some y in X, nothing more general. Okay. Then I need the second piece of data. So now that's already what we do. So we consider H is a collection of smooth, cooriented hypersurfaces in some manifold X. And we call them HI.
Sorry, X is three-dimensional.
X is no.
It's hypersurface. Sorry.
Yeah, it will be sometimes three-dimensional, sometimes two-dimensional. We will never go to anything more complicated. So this is HI, and now this is an important definition. So I want to consider Lagrangian assigned to this data called L, or what is the same, L assigned to H. So this is the following thing. So you take the zero section of your X, called X0, and you add to this all cotangent bundles, oriented cotangent bundles, because HI are cooriented to this X. And so this all sits inside of the cotangent bundle to your manifold. Okay, so that's the Lagrangian. This is the key Lagrangian. And because my condition on hypersurfaces, I actually didn't formulate the yet condition, but hypersurfaces are smooth, but they can intersect. And the whole point will be how they intersect. But the general expectations tell you that there is some subcategory C1L, which leaves, it's actually not sheaf of categories, but I'm talking already about some category, which is a section of this sheaf of categories. You take the sheaf of categories, you take a section of the whole L, and it sits inside of the category CL evaluated on L itself. Okay, so now what are the conditions? So this is, what is this? This is sheaves on, let's call the sheaves F. On X, such that if you consider any of these hypersurfaces, but not zero section, then if you consider microlocalization factor of this F, then and you restrict this, you take macrolocalization on this cotangent bundle to this HI minus zero section. Then the condition is that this is a rank 1 local system. And this is a place where non-commutative can come, because you can consider now, so your surfaces and threefold, they're usual thing, but you can take some non-commutative field, like n by n matrices. You can pretend it's a field if you want. You can do something like that, consider this field like quaternions, call it R, and then consider conditions that you work with sheaf of R local system, with R sheaves, and these microlocalizations rank 1 R local system. Okay?
That's just kind of a thing, part of the story in dimension 2, which I understand better. And for people, symplectic topologists, if you take a Riemann surface and your collection of divisors, it's, for example, you take finitely many points and collection of non-intersecting closed curves about this point, then you can look for positive conormals, which sits in
the normals of whom, Jan?
Of these brown or whatever curves, which
Curves.
you wrote, half of cylinders, yeah?
Yes, exactly.
In the cotangent bundle, okay. And then you take rank 1 local system, so they are objects of the Fukaya category of the cotangent bundle. It's or rather subcategory generated by this conormal. So that's an example, and it can be, of course, described as a category of certain sheaves on a surface whose microlocal support belongs to this.
Yeah, but I want to keep
conormal.
I want to keep elementary, so I pretend I never heard about Fukaya category.
Yeah, but people, you see, the things which are elementary for you may be non-elementary, like Steinberg symbols, whatever, may be non-elementary for some people in the audience, but Fukaya category, it's for some other people are elementary. So you see,
Not elementary, I believe, but at least people used to it. Okay, but I pretend I never heard this word. So now what I want to say is that finally, I just described that I take this complexes of constructible sheaves with jump over these hypersurfaces. But finally, I want to consider the category I'm looking for. This is subcategory of complexes of constructible sheaves here. So we defined with Maxim, and I'm not going to tell you the definition. This is subcategory.
You had, it's another, you have already, so I'm confused with your notation above, where the inclusion was in the
yeah. You absolutely, this is really horrible. I don't know what to do with this. So maybe I do something like that. So, but maybe I just change the color. You're right. So I already use this notation, unfortunately. So now I make it kind of script, as in the text, and different color. And so now it less reasons to complain. But you're absolutely right. It's just abuse of notation. But I consider some subcategory of these complexes of sheaves, constructible sheaves, we jump over this HIs and also local system around opens on the best. But so they're somehow defined. How they defined doesn't matter. But I want to give you one example where this definition leads you precisely to where we before. So if I take, and this is basically what you said, Jan, but so if I draw this picture larger, so if you had take a surface, smooth surface, and you consider now these hypersurfaces, which are just curves, and you consider there is a puncture on the surface, and around every puncture, I take m little concentric circles like that. So in this situation, m equals to 2. Then in this case, basically, if you compare definitions, you will see that the moduli space, which I didn't introduce, I introduce this in a second, but it's going to be precisely the space which appeared in the motivational part. So it's X, G, L, M, S, the space of local systems on the bulk, which has filtrations near each puncture. So this will appear as some moduli space, which I'm going to introduce now. Now, what is this moduli space?
Yeah, just kind of a small remark because there was, yeah, that's Betty side of the Riemann-Hilbert correspondence of Deligne-Malgrange Riemann-Hilbert correspondence. So you have irregular, like meromorphic connections if you introduce complex structure. And so then you can reformulate whatever they constructed in this term. So it's just for those who knows. Yeah.
But actually, not quite, because I'm talking about this X is indeed it's some Betty moduli space, but it somehow relates to local systems on a punctured surface with this data, yes, but
yeah, I think we actually we worked out this two-dimensional example with Maxim as part of this Riemann-Hilbert story. Maybe there is some minor difference, but it's strange because our Betty side was cluster and it coincided with the Streumann Schende Zaslow. If yours coincide, they should be isomorphic.
so this moduli space precisely with this data is taken from our paper with Fock. That's precisely this moduli space of local
Yeah,
systems
but I
with
mean
filtrations.
just the relation to the other, to the drum side.
And this is taken, for me at least, it's taken from our first paper with Maxim. And this subcategory of H-admissible DG sheaves was introduced in such a way. Let me give you the definition and then we start.
Yeah, go ahead. Yeah.
So if you take, so I wanted to introduce some moduli space called X related to Lagrangian. And you can also say that this is X related to your collection of hypersurfaces. And this is just a derived stack of objects in that category. Which is CL. Now, what's important here that if I just consider sheaves with constructible sheaves with rank 1 localization and so on, so I in principle can get complexes of local systems anywhere on the surface, and I need a definition which actually doesn't give me this. And so there is some way to cut the category quite dramatically so that what I get in this situation is precisely this and nothing else. So this is this moduli space XL. But if I have boundary of the Lagrangian, I surely have the same moduli space related to the boundary of the Lagrangian. And I'm surely have the restriction map from one category to another category. So this is all which I need from this background about symplectic topology. Now let me go to cluster structures. So now I'm going to introduce a kind of main definition. So I say that a collection, it's a definition. So the question is how you introduce this families of hypersurfaces which give you something which deserves to be called cluster Lagrangian. And so here is the answer. So we say that a collection, it's a definition. Called H of smooth cooriented hypersurfaces in m-dimensional manifold. The definition is general, but m is not going to be bigger than 3. So we call this manifold X is, and now the word is a Q diagram. If the intersection points in general transversal, so the intersection points where k less than m hypersurfaces intersect. So this is transversal. And the only thing which is not transversal can happen at finitely many points. So there are two conditions. So the remaining isolated intersection points so let's call them Q, are intersections of m+1 hypersurfaces. But that's not all. And the important crucial condition is that moving any of this, moving any hypersurface, let's call it H, which contains point Q, we're talking about some intersection point Q, away following its coorientation. We arrive to cooriented out simplex. So that's a strange definition. Now let's see. So first of all, is it clear formally what I said? Or maybe I give you first example. So you can take example when manifold is one-dimensional, but let me start with a case when m equals 2. And so if m
you
equals
mean
2,
simplex will be literally simplex. You will have like 4.
Exactly. But this will be in 3 dimensions, but I'm talking about 2 dimensions.
Okay.
It will be triangle. Let me give you an example. So in this case, this object is known, and it's called triple crossing diagrams. And it consists of collection of lines which are cooriented, or in this case, I can say oriented, because it's the same thing if the surface is oriented. And they intersect only at one point. The intersections are single points. It could be other intersections, of course. And at this single point, their orientation is like that. Nothing else. So I cannot, for example, put orientation here. This will violate my condition. So they're like that. And what is nice about this geometric objects, and this goes back to our work with Kenyon, so where we investigate this kind of things. So, but it's very, very easy observation. So if you consider class of objects like that with some minimality condition, then this is also the same thing to what we called alternating diagrams. An alternating diagram, as the name suggests, something like that. So you have again oriented curves. And then if you consider the other curves which intersect them, then their orientations alternate on the way. So for any curve of your family, the intersections of the other curves of the family supposed to alternate.
So
and then how
it's actually one-dimensional story, collection of points on the line.
Of course, yes, of course. So the notion of alternating diagram can be generalized to n-dimensional space, and dimension 1, you get precisely what Jan said. You get collection of points which are cooriented this way. Yes, this is part of the definition if you want. But okay, so and how you go from here to here? You just move your one of these lines in the direction prescribed, and then you'll get precisely alternating diagram. Now, why this is the same thing? Because if you consider these alternating diagrams, there are actually I prefer to put orientation, just more convenient for me to draw the other way. So if I do it this way, then I immediately see that I have some pieces which is cooriented counterclockwise like this. And then I also see that there are some pieces which are oriented clockwise. And I can get them here if I put one more line. But I also have a third kind of pieces which we call mixed. So this is mixed. So all domains are of three types. So they are either mixed or black or white or blue or green. So three colors. And how you go back? So one way I said this is deformation. The other way, you have to shrink the points which are blue. And then if you think what happens, you'll get precisely triple crossing diagram. But another thing which is equally nice, that the same object is also well known, and it's called bipartite ribbon graphs. So this is three objects which are the same geometrically. Now, what is bipartite graph? So you have graph which has vertices which are black and white. And they have something which we call zigzag passes. This is the passes, they are zigzag, so they are turn right at black and red and left at white. And then if you draw them, then you will see that you get something like that. And then the statement is that this collection of zigzag curves is an alternating diagram. Okay, and then we are in the cluster setup because actually that's what we are doing in commutative case with canyons. So we said that if we consider bipartite graphs and we consider this family of zigzag passes, okay, let me say it this way. We associated to bipartite graphs certain cluster Poisson variety, this with canyon. And one can later one can see that that's precisely this moduli space which corresponds to collection of curves, which is this alternating collection. So they're just the same thing. But since time is a little short, I want to give you the main example, which is explaining what happens in dimension 3. So in dimension 3, so let's see what is a Q diagram in dimension 3. Now, dimension of X is 3. And then there is a main example. So we called basic Q diagram. And you think about this as follows. So you take a cube. Takes some time to draw cube when you do this iPad. And then this cube itself, so you take cube, I call it cube C. So this is cube. But if you take the boundary of C, so this cube is something three-dimensional. It's cube in 3 dimensions. If you take boundary of C, it's two-dimensional, but it carries natural bipartite graph, because if you say that these vertices are white or blue, then you can declare the other vertices. Oh, sorry, I did something wrong. Okay, so you have 4 vertices which are staying apart, not connected by. So first of all, you have a graph. I said bipartite graph. The graph is, of course, the edges of the cube. This is, of course, graph on the surface, so it's a ribbon graph. But now its bipartite structure is unique up to rotation, and so the vertices of different colors are those ones. Okay, so this is a bipartite graph. Now, how to assign to this Q diagram? I will produce 4 planes inside of this cube. And so these 4 planes are
orthogonal to 4 main diagonals.
Of course, yes, but not just that. They are central, meaning the cube has a center. The cube has a center. And then, as Jan said, and I agree, there are 4 diagonals. So the central planes which are perpendicular to, as Jan said, cube diagonals. And oriented, remember that we have to have orientation. So they are cooriented, but the orientation of the diagonals is supposed to be like that. You take the one which you prefer, it doesn't matter, but you have to be consistent. So if you orient them in a certain way, for example, from blue to red, then your planes are cooriented and they intersect at a single point. I can try to draw what you get, although it's a little challenging. So you get something like that as a section. So this way. So it's a hexagon.
4 of them.
And you have 4 of them, and they intersect at one point. So this is the analog of this triple crossing diagram. And this is typical Q diagram. Why Q? Because this is a quadruple intersection. That's why called Q diagram. No better name found. And this is the simplest possible non-trivial Q diagram. Now, the general idea that these Q diagrams are 2D analogs of bipartite graphs. Bipartite graphs or whatever of these 3 objects. So they produce the alternating diagram of surfaces, or you can think about this as this kind of Q diagrams. Now, let's just investigate what we get in this case. So going to back to the beginning of talk, so I'm supposed to have M, which is a threefold, and this M is going to be just a cube C. So this is my threefold. Now I have boundary of M, and this is, of course, boundary of cube. Now I have my Q diagram, and what I can do, I can intersect it with the boundary of my manifold. So what I'm saying, you can do this for any 3-dimensional manifold. You can take any 3-dimensional manifold, you assume that you have some Q diagram which lives in this manifold. I just defined what Q diagrams are. And then you can intersect this Q diagram with boundary of M. And I assume that this is alternating diagram. It's maybe not true, but usually, I mean, typically it's okay. And then I have situation when I have this threefold with Q diagram, and on the boundary you have alternating diagram. Okay, then as we discussed before, I have the category, and this category in this particular case will be category related to this diagram, Q diagram, in this case on the cube. And I have restriction functor which takes us to the category related to the this bipartite graph which I just introduced. This is a full example now. So I consider a situation when my microlocal supports are one-dimensional local systems, and I insist they're trivial. That's a condition. This is like before I was saying that I consider local systems with unipotent monodromy. This is a correct way to formulate this in this setup. And here, if I'm general manifold, I have to put conditions that my sheaves on this surface are trivial, but for cubes, they're just disks, so they're trivial anyway. And now I go to the other crucial definition of the story. So this thing, that's how my Lagrangian is going to look like, because what's going to happen that I take the image of the restriction functor applied to this moduli space, in this case is a Q cube, and this will lift inside of this space. And you can do this in general. And this space in ours, it's always symplectic. This is part of the two-dimensional story. And in our case, it's actually two-dimensional, if you think about this, if you over complex numbers. And the claim that this is always going to be Lagrangian, that's not the key point. The key point that this is a cluster Lagrangian. In commutative case, it's going to be K2 Lagrangian. So this means that I would be able to define this one-dimensional curve, maybe non-commutative, in this two-dimensional thing just by explicit equations. And in general, so I defined what Q diagrams are, and the point is that the intersection points are the ones which give you this description of this cluster Lagrangians. They give you the equations by which you define this cluster Lagrangians, and they correspond to these dilogarithms which appeared before. But now let me finish with this example. So I need to draw this cube again. Okay, maybe I draw it again. I want to explain what the equations are. And this is the analog of Steinbeck relations. Okay, so I have such a cube. And then I want to draw on this cube one zigzag path. So it goes as follows. So it's green, oriented, and this is one zigzag path on this bipartite graph I was talking about. So it goes like that. Okay, call it gamma 0. Then I also have on this cube the vertex, which is across the zigzag path, so it's called V. And then I have, so I have a local system on this graph. This is just edges of the cube. And I have a condition that on each zigzag path is trivial. That's a condition. And then I can consider monodromies of this local system, and I will just draw them. So you can have monodromy when you go around the cube this way. So you always start at vertex V and go around the square. So you get one monodromy. If you do it with a different face, you get another monodromy. And here you have the third monodromy. And I label them like X, Y, and Z. this is my monodromies. And so this, let me just write it, this X, Y, Z monodromies around faces sharing V. And if I'm in a non-commutative situation, what is monodromy? Monodromy, for example, X or maybe Y or maybe Z, they're endomorphisms of this bundle, of this fiber of my one-dimensional local system. So just in commutative situations, they're just numbers, but in general, they're just endomorphisms of rank 1 R model. Okay, so then the theorem is that this restriction is fully faithful in this case for the cube, restriction to the boundary of cube. Fully faithful embedding, but the key point is the following, that if I consider Lagrangian, now what is a Lagrangian? So let me just say what the definition is. So now remember that I have Q diagram which lives inside of this cube. And I consider now all these admissible Dij sheaves, which are complexes of sheaves, which on the complements to these four planes are just complexes of local systems, and there is some condition in which degree they can sit. But they jump over these four planes in the sense that the microlocalization is going to be rank 1 local system which sits on this plane. But most importantly, I don't put any conditions to what happens here. What happens in the center, this point Q, I don't specify. So I only know that this microlocalization, each of these planes here, it's one-dimensional local systems and no conditions inside. Then the statement is that the space, the moduli space of all sheaves which this microlocal support and these conditions is actually Lagrangian, which is described by the following equation. So this is Lagrangian. Lagrangian where? In this moduli space, we talked about this moduli space here, of local systems on this cube, which are trivial along non-trivial loops. So it's Lagrangian this X 1 on this gamma cube, which is set in complex numbers two-dimensional, so this of complex numbers is one-dimensional, and it's given by the following equations. So the equations are the following. So if you take x1, x2, x3 plus x2, x3 plus x3, this equals to 0. And also if you take x1, x2, x3, this equals to -1. So these are the equations. And if you want to do example, when you assume that R is a field of complex numbers, then this equations looks as follows. So you can just do it in a different color, that you have the commutative, like x1, x2, x3. Different color and small letters just means that you have complex numbers in commutative situation. Plus x3 equals to 1, that's the equation, because x1 to x2, x3 is -1. Then the Poisson, the symplectic structure is d log, let's say x2, which d log x3. And then if you consider element, if you consider the Poisson bracket, which relates, oh, it's small. So this bracket of Poisson bracket or bracket, and I can write this also as wedge product. So this is what? This is just minus x2. And what is x3? x3 is 1 plus x2, if you think about this. 1 plus x2. And so that's precisely the Steinberg relation. So this is 0 in K2. Because you can solve this equation. So you look at this equation, so you solve this equation, and so you see that x3 is actually 1 divided by 1 plus x2. And that's why you get the minus sign. But other than that, we reproduced Steinberg relation. And so this basic Q diagram tell us what is non-commutative Steinberg relation. And it describes this Lagrangian in this case. Now, my time is, it's very much over. But let me just say what happens in general. So in general, what happens is the following, that I have my Q diagram in the space. And this Q diagram, it produces some Lagrangian. And this Lagrangian, near those intersection points, I see little cubes. I skip some part of the definition and take my Lagrangian, and I actually delete some balls around their intersection points. Then I see these cubes. And I maybe see it somewhere else. And all in all, so my Lagrangian looks as follows. So I have the original Lagrangian L, which I defined before, which corresponds to Q diagram. Then and this lives in my manifold M. Then I have boundary of my manifold. And in the boundary of my manifold, so my manifold, I draw it somehow here, dm and m. But I have some kind of alternating diagram here. But then if I consider, there's one thing I wanted to say, which is crucial. So I want to introduce a second Lagrangian, L0Q. This is the first one, minus, so I remove 0 sections over mixed domains. It's a crucial step. And mixed domains are the ones which are neither black nor white. You can do this in 3 dimensions also. So if I remove this, then I get this another Lagrangian, and it has just singularities, singular points, which corresponds to the original intersection points on the manifold. And so I remove little disks about this around the singular points. And then what I see precisely this picture. So I have some kind of threefold, which has boundary, which I already described. This is my cubes, boundary of my cubes. And then it has some boundary which corresponds to boundary of the manifold. And if you see here alternating diagram, which we call DQ, then what you see here is actually some spectral surface which corresponds to this alternating diagram. There is such thing. And so now I get Lagrangian, which has boundary of 2 types, this cubes and the spectral surface of the alternating diagram on the cube. And then it's very easy to describe sheaves which lives on the bulk. It's basically local systems again on some graph. So it's just a very easy description. They're described by the monodromy, so the loops of this graph. But then what I'm interested in what they cut on this space spectral curve, because that's precisely the cluster in my non-commutative Poisson space. But the answer is obtained as follows. To understand what I get, I consider bigger surface where I add these boundaries here, and then I get Lagrangian here. And then I just take the description which I have of this bulk and impose condition for each intersection point. And so I get system of equations, and that precisely this cluster system of equations which describes the restriction to the boundary of my moduli space. So that's it. So the example which I said in the beginning is a crucial example, and just having just this example, you get cluster description of this Lagrangian. So maybe I should stop here. The other comment is that the examples I was talking about in the beginning, this X, GLM, S, and Lagrangians there, they can be described this way, and this is not quite trivial and requires some construction, but I'm not talking about this. Okay.
Okay, all right. Thank you. So, are there any questions? Sasha, I have kind of question which is motivated by two-dimensional story, which is much simpler, of course, but at least I understand the drum side and how to generalize it. You consider your cotangent bundles always having 3D manifold. You produce some kind of Calabi-Yau six-dimensional, which is a cotangent bundle to your 3D. Do I understand correctly?
Wait. Let me just repeat what you said. You said, let's consider cotangent bundle to three.
No. It's not me. It's you. I mean, do you double your three-dimension? Do you consider cotangent bundle to your 3D manifold at any point? Or
no, the main object is that my Lagrangian lives in the cotangent bundle to this three-dimensional manifold. On any manifold, it's the same. If you have hypersurfaces, take conormal, they live in cotangent bundle.
Yeah, but that's exactly the point which I'm asking about possible generalization, because in 2D story, as you know very well, you can replace cotangent bundles by more general, whatever, I don't know, symplectic manifolds with open leaves, which are not necessarily cotangent bundle, like cotangent bundle to a Riemann surface, which you discussed at some point. Yeah, it's four-dimensional. And you can consider another four-dimensional symplectic manifold, which is a torus C star square, which is cluster from itself, and you start to think about it as a cotangent bundle. And I understand what is the Dram and Betty side that story, but I
of the
do not
Fukaya category.
In terms of the Fukaya category, but the fact that this Fukaya category can be described in terms of constructible sheaves like microlocals, it's a conjecture. It's not proven. So then you always produce, in the case of tangent bundle, you always produce in terms of this DG whatever admissible.
This is constructible sheaves with certain very strange looking conditions.
Yeah, but if I kind of take another six-dimensional, symplectic manifold, like three-dimensional complex cube, like C star in the power 3.
Right.
So from real point of view, it's somehow cotangent bundle to the three. Yeah, but is there an analog of your story?
I think yes. And to think about this, the first thing you should ask yourself, okay, this is this three-dimensional Lagrangian, but how it looks like. Returning back to the surface, so we get two-dimensional Lagrangian in four-dimensional symplectic space. And then the key point was that there are pieces of this Lagrangian which actually those spectral surfaces. That's where bipartite graph plays a crucial role. Any bipartite graph provides you such an open torus, and that's the cluster structure. So here again, we have this Lagrangian, which is conormal bundles to this surfaces plus zero section. And if I again remove zero sections of the mixed domains, I get again some kind of Lagrangian which produce me cluster. But this Lagrangian is no longer non-singular. So before it was spectral surface, so it's a non-singular two-dimensional manifold. Now it's three-dimensional, but it has singularities, precisely one singularity corresponding to each of this Q intersection. And when you have a singularity of any manifold, you can line on some other manifold. You can ask what kind of singularity by considering link of the singularity. So in this case, you get some surface. And so it turns out that what I get here is a torus with 4 holes. So that's a kind of topological structure of this Lagrangian I'm talking about here. And it should be possible to define this in general terms, but we were doing this in this example. But I'm pretty sure that there is kind of more general definition.
Okay.
But the key point, at least my key point here, that bipartite graphs, which different people like for different reasons, have a two-dimensional analog. And it seems to be that it is as rich as its one-dimensional cousin.
More questions? Then, Sasha, I will ask you to send me now your notes.
Okay.
Yeah. And so we will add them to the video.
Okay. Okay.
Okay, thank you very much. It's a very interesting talk. And as you said, there is a paper. And so
What?
people,
Oh, yes,
there is a
paper.
paper in the archive, and
Yes.
even two, if, well.
Can I ask a question?
Yeah, Ilya, yeah.
You just said last thing which trigged my attention about this link being a torus and this singularity. I know if one thing, if you take this 4-valent curve, like, you know...
Sorry, Ilya, I don't hear you well. So can you go, first of all, wait a second, slowly and maybe a little louder.
I know one place where this singularity comes as a singularity of a Lagrangian. If you take a 4-valent graph, like one vertex and 4 rays in R3, and then you put on every ray, you put a conormal. And then there is a way to fill it over the vertex to make it into like this singular Lagrangian, and that's precisely the what you said. It's the link over the two torus.
Yeah, and that's how it appears.
I see.
But why this example is important for you?
I just was trying at some point construct this Lagrangian, just given some tropical cycle, try to lift it to something like Lagrangian upstairs in this cotangent bundle.
Okay, so but the way the story appears is like you have a boundary. On the boundary you have this bipartite graph, and it has this zigzag passes, and then you start shrinking your boundary when it goes. Let's suppose that at the center you have some black hole, so you start shrinking your boundary, and then it's very clear what's going on every moment before you go to the center, because you just have this conormal bundles on those surfaces, and you have one-dimensional family of them. But then, if you want to describe what happens in this decisive moment, that's exactly what happens here.
I understand. Okay.
Is this kind of the same in your picture?
I think it should be the same, yeah.
But the question is why it's important for you.
I don't know, but I said it's kind of interesting that you don't get a smoothable Lagrangian because you wanted something.
It's not smoothable, it's singular.
Yeah, that's what I'm saying.
But also remember that I was talking about these Q diagrams. There was a strange conditions that if you move one of the surfaces, then you get simplex cooriented out. You can consider other coorientations, and they don't give you something very tractable. At least this nice description, it uses decisively this fact of three-dimensional geometry that you get a simplex cooriented out. Somehow it plays important role in what's going on.
I'll have to study more maybe. All right, but thank you for a very wonderful talk, Sasha.
Yeah, okay, so there are at least two of us. All right, thank you, Sasha, and I remind you about your notes. Okay, thank you very much, and this is it for today. Thanks to those who came here.